Alright, welcome to the next page. We're going to talk about Bernoulli's equation. Alright, and so say we have a differential equation dy over dx plus p of xy, or p of x times y equals f of x times y to the n, where n is any real number, is called Bernoulli's equation. Note that for n equals 0 and n equals 1, this equation is linear. Now, if we look at the equation the way that it's represented, this looks very similar to linear equations, which is section 2.3, where we found an integrating factor and solved it that way. We're kind of doing the same thing. We're going to be given an equation that looks very similar to being linear. What makes this not linear is this part right here, that y to the n. Now again, it can't be any power greater than 1 or less than 0 in order for it to be linear. So it can only be 0 and 1 for it to be linear. And because that it's going to be a number that's, not going to be 0 or 1, then what we're going to do is we're going to do another u substitution, but we're going to do u is equal to 1 is equal to y to the 1 minus n power. All right, we're going to multiply that through, and we're going to be able to reduce Bernoulli's equation to a linear equation. Once we reduce it to a linear equation, then we can go ahead and solve. So this isn't that bad. We just realized, okay, we got to find our u substitution, and we're just going to substitute that in. Now, we want to make sure that when we start, we have dy over dx is in front. So if it's not of that format, we're going to make sure that we try to get rid of that first. Well, this one is. So now what we're going to do is we're going to focus on that y to the nth power on the other side. So here we have y e to the xy squared. So n, since n is equal to 2, our u substitution is just going to be y to the 1 minus 2 power, which is just y to the negative 1. So if u is equal to y to the negative 1, we can also say that y is equal to u to the negative 1. Now, when we're doing this and we have things in terms of y, to get u, it could have been, it could be in terms of x. And so say, hey, we want to find what dy over dx is. So what we're going to do is we're going to say, okay, well, dy over dx is just, now we have u to the negative 1. So what we're going to do is we're going to have to go through, u to get to x. So we'll have dy over du is equal, not equal to, but times du over dx. Now we know what dy over du is. This is taking the derivative of u to the negative 1. So it's going to be negative u to the negative 2, but then we don't have du over dx. But it's okay because we'll be able to write our equation. So now we have all of our substitutions that we need. We have dy over dx, and we also have, wherever there's a y, we can substitute in the u to the negative 1. All right, so let's go ahead and do that. So we're going to take our equation, and we're going to go ahead and do some substitutions. So dy over dx is now negative u to the negative 2 du over dx minus y. Well, now our y is u to the negative 1, and that's equal to e to the x. Now y squared, what did we say y was? U to the negative 1 is going to be u to the negative 2. Now, just like we want dy over dx by itself, we're trying to turn this into a linear equation, so we want du over dx by itself. So we're going to divide everything by negative u over negative 2. All right, so let's go ahead and do that. So when we do this, that first part's going to be du over dx is equal to negative divided by negative is going to be a positive, and that's really multiplying by u. So, I put an equal sign there. So it's going to be plus just u to the first power, all right, because it's like multiplying by u squared. The u to the negative 2's are going to cancel each other out, and we're just left with negative e to the x on the right-hand side. Now, this is a linear equation where it's of this format, and in order to solve a linear equation, what we wanted to do was find that integrating factor. What we want is this apart. E to the integral of p of x dx. Well, remember, p of x is always that part that's in front of, usually in front of y, but now since u is our dependent variable, it's going to be whatever's in front of u. So in this case, it's 1. So our integrating factor here is going to be e to the integral of 1 dx, which is just going to be e to the x. So we multiply the left-hand side by e to the x times u. And then again, that part's going to cancel out on the left-hand side, so we don't need to worry about, writing the integral. If you need to see it, we were able, it died again. What we were able to do was we were able to pull it apart using the product rule, and then we would have the derivative equal that. So on the left-hand side, it's just going to be e to the xu. But on the right-hand side, we're going to multiply by the integrating factor. So I have negative e to the x, and then I'm going to multiply that by an e to the x. So I'm going to have negative e to the x times e to the x, and then I'm going to have to take the integral of that with respect to dx. E to the xu is going to be on the left-hand side. We're going to be left with negative. We'll keep the negative on the outside. E to the 2x dx. We'll integrate that. We'll get negative 1/2 e to the 2x dx. Nope, got rid of the dx when I took the integral. On the left-hand side, I get e to the x. U, divide both sides by e to the x. So u is equal to negative 1/2 e to the x. Got my c there, so plus c e to the negative x, so divided by x. Let's substitute in for our u. Our u is y to the negative 1, and that's going to be equal to negative 1/2 e to the x plus c e to the negative x. And we're finished there. We could clean this up, but why would we want to clean it up? Because it would be 1/y. We'd have to, do the reciprocal of the left and right side, and that's not worth doing. So we can be finished right here.